Chemical reactions are dependent upon the properties and structures of the molecules involved, and an easy way to predict the structure of the molecules is to draw Lewis dot diagrams. I want to show you how to do Lewis dot structures for molecules, but before I do that, I want to show you how to do them for single atoms to make sure you understand that first. Please note that everything I'm going over today, including this document, will be in the notes below, so you don't have to scramble to copy everything down as I'm talking. As we know from past lessons, the electron configuration of nitrogen is helium, 2s2, 2p3, and therefore the orbital diagram looks like this. That tells us that the valence shell of nitrogen is 2s2, 2p3, which means it has a total of 5 valence electrons because we add together the exponents in the valence shell. There's a quicker way to do this than having to do the electron configuration or the orbital diagram. We could just look at the periodic table. If we look here at the periodic table, we see that nitrogen is in group 5, and we just said that nitrogen had 5 valence electrons. That means that everything in group 5 is going to have 5 valence electrons, and by that logic, everything in group 3 will have 3 valence electrons, everything in group 4 will have 4 valence electrons, and so on. Now that we know that nitrogen has 4 valence electrons, we're going to go ahead and attempt to draw them in a Lewis dot. When we're drawing our Lewis dot structure, we only have 4 regions to work with, the top and bottom and the right and left. Because we have 5 dots we need to draw, it's obvious that we're going to have to double some of them up. And you can see here in my Lewis diagram, I do in fact have a pair of electrons here on the right. That correlates with the fact that in the orbital diagram, I have a pair of arrows, and then the 3 unpaired electrons correlates with the 3 unpaired arrows in the 2p3. So it makes sense. Side note, it really doesn't matter where I draw that paired set of electrons. I could put them on the top or the left or the bottom. It doesn't matter where it is located exactly. If you look here at this revised version of the periodic table, you can see that all of the atoms in group 5 have the same Lewis dot structure as nitrogen because they have the same number of valence electrons. That's true for each of the groups. For example, everything in group 3 has the same Lewis dot structure. So go ahead and get out your periodic table and let's practice a few together. Phosphorus is in group 5, like nitrogen, so it also has 5 valence electrons. So we're going to go ahead and write our 5, and because I only have 4 spots but I have 5, I will have to double a setup. Hydrogen is in group 1. So we go ahead and just give it 1 valence electron. Pretty easy. Oxygen is in group 6. So we go ahead and give it its 6. Notice I am going to have to double 2 of them up. And again, it doesn't really matter where I draw these as long as you have the correct number. Sulfur is in the same group as oxygen, so we would anticipate that it should look the same. Fluorine is in group 7, so it has 7 valence electrons. Go ahead and draw the 7, and you're going to have to pair up. Chlorine is in the same group as fluorine, so it makes sense that its Lewis dot structure should look the same as fluorine. Not too bad when it comes to doing single atoms. Let's talk about how we apply that principle to drawing Lewis dot structures for molecules. In the beginning, I'm going to have the steps side by side with the examples, and I'll work through to show you the steps as we follow them. So our first step is to count the number of valence electrons for each element. So if I look at the periodic table, I see that phosphorus has 5 valence electrons and hydrogen has 1. In the compound pH3, if I have 1 phosphorus and 3 hydrogens, that adds together for a total of 8 valence electrons. I just took care of steps 1 and 2. Step 3. I'm going to put the least electronegative atom in the central, as the central atom. So I'm going to put it in the center. I know the least electronegative because electronegativity decreases as I go down a group or as I go from right to left across a period. Not only that, I have a note here that hydrogen can never be the central atom. So that means that phosphorus is the central atom, and I'm going to go ahead on to step 4, which means I'm going to draw a skeletal structure. I'm going to write the remaining atoms around phosphorus, drawing a single line connecting them to phosphorus. Each single line represents a single bond, which involves 2 valence electrons. All of this is noted in step 4. Now I'm going to go ahead and complete the octets for the outer atoms, but please note that hydrogen, which is in the first period, doesn't actually follow the octet rule, which means it has 8 electrons. It follows the duplet rule, which means it only has 2. And since we already said that the single line represents 2 valence electrons, hydrogen already has its 2 in each of these cases. So I don't actually need to complete the octet of the outer atoms in this case. So step 5 doesn't need to be done. Moving on to step 6, I do need to complete the octet of the central atom, in this case phosphorus, by drawing dots. Now I have given phosphorus its total of 8 because it has 3 single lines and 2 dots for a total of 8. So it meets the octet rule. Now in step 7, I'm going to count the sum of the electrons in the structure. Like I just said, if I have 3 bonds and each one is worth 2 valence electrons, that's 6. And I have 2 dots, each worth 1 valence electron, so that's 2. 6 plus 2 does add up to 8, and that matches with the total number of valence electrons we calculated in step 2. That tells me that my valence structure is complete. My Lewis dot structure is complete. Let's go ahead and try it with another one. I'm going to zoom out a little bit. Sorry, I know this is probably pretty small, but I'll zoom back in a little while later. All right, so our first step is to count the valence electrons. So if I have 1 bromine with 7 valence electrons, 3 oxygen with 6 valence electrons each, and 1 negative charge, which accounts for 1 electron, when I add all of these together, I get a total of 26. Notice what I said here about if it is an ion. Now I'm going to put the one that is in the most electronegative in the center. The least electronegative in the center. And also it's the one that there's only one of. And then I'm going to go ahead and write the 3 oxygens around it connected by a single bond. Then I'm going to go through the process of completing the octet for the outer ones. So I'm going to go ahead and give all of these oxygens 8 because the bond already accounts for 2 electrons, and then each dot accounts for 1 valence electron. So now each of these oxygens has completed the octet rule. Then I'm going to go ahead and do the octet for the central by giving it 2 dots. And now bromine also has fulfilled the octet rule. Now I'm on step 7. I'm going to count the sum of all the electrons in this structure. If I have 3 lines which each represent 2 valence electrons, that's 6. And then I also have 20 dots altogether. 20 plus the 6 adds up to 26, so this structure is complete. The only thing that we really should do, because it is an ion, is we should put brackets around it and put a negative charge here. Also, if you want to remove these circles here, these are more so just for us to see that the octet rule is complete, but generally we don't draw those circles in the diagram. Let's go ahead and move on to SO3, and you're going to see in SO3 that I'm going to have to do a little bit of extra at the end because something's going to happen. Our first step is the same, count up the total. I have 1 sulfur with 6 valence electrons and 3 oxygens with 6 valence electrons each. That gives me a total, of 24. I'm going to put the least electronegative in the middle. In this case, according to the periodic table, it is oxygen, and I'm going to connect them by a single bond. I'm going to go complete the octets for all of the outer atoms by giving each one 6 dots, which when you add it with a single line adds up to a total of 8 valence electrons, which is the octet rule. I'm also going to complete the octet for the central atom. Since it already has 3 single bonds, each worth 2 valence electrons, it just needs 2 dots for a total of 8. Now I'm on step 7. I'm going to go ahead and count everything up. If I have 3 lines, each for 2 valence electrons, that's 6. And altogether here I have 20 dots. That gives me a total of 26. Well, I'm only supposed to have 24. So you'll see here in step 8a, if the sum of the electrons in the structure is more than the total valence electrons of the molecule, here's what you need to do. You're going to erase a pair of the electrons on one of the outer atoms and on the central atom, and you're going to make the bond between them a double bond instead. This means that the oxygen here still fulfills the octet rule and the sulfur still fulfills the octet rule. So I'm still good in that regard. Now let me go ahead and count everything up again. I have 4 lines here for a total of 8 electrons, and now I have 18 dots, which gives me a total of 24. So now my structure is correct. Notice that I could have erased the valence electrons from one of the other oxygens. I didn't necessarily have to choose that one on the right. And that is possible, and that's the basis of another part of chemistry which involves resonance structures, which is beyond the scope of this tutorial, but I do just want to point that out to you. All right, this next one is CO. It's a little covered up by the valence electrons I drew. I'm going to go ahead and zoom in now that we somewhat understand the steps so that we can do this one a little closer up. C, there's only one of them, and that has 4 valence electrons, and oxygen, there's only one with 6 valence electrons for a total of 10. In this case, I don't need to put one in the middle because there's only 2 atoms I'm dealing with. But I am going to connect them by a single bond. Then I'm going to go ahead and fill in the octets for each one of them and count how many I currently have. I have 1 single bond and 12 dots. That gives me a total of 14. I'm only supposed to have 10. So what I'm going to do now is I'm going to erase a pair on the oxygen, and there's no central atom here, so the only option I have is to erase it on the carbon, and instead I'm going to change that to a double bond. The carbon still fulfills the octet rule, and so does the oxygen. Let's go ahead and count. I have 2 lines for a total of 4 electrons, and altogether I have 8 dots. That gives me a total of 12. I'm only supposed to have 10. So I need to repeat that process. I'm going to again erase dots on an outer and quote-unquote the central, and I'm going to now make it a triple bond, and then I count again. A triple bond, 3 lines, accounts for 6 electrons, and then I have 4 dots. 6 and 4 adds up to 10, and now my structure is complete. So here in this phase of creating the Lewis dots, I say here that if you end up with a sum that's more than the total you should have, you have to erase and create a double bond, recount. You got to keep going, and if you run out of places to make a double bond, you have to erase and make a triple bond. That's what we say here. And recount. All right, let's take a look at this one. Again, sorry that my dots got in the way, but that's okay. We can figure it out. It's CH2. So carbon, there's 1 with 4 valence electrons. Hydrogen, there's 2 with 1 each. Oxygen, there's 1 with 6. Altogether, I have a total of 12 I'm working with. Carbon is the least electronegative, so I'm going to put that in the middle, and I'm going to draw lines connecting. I'm going to fill the octet for the oxygen only because remember, hydrogen is one of the ones that has an exception. It is only a duplet. Now I'm going to go ahead and count how many I have. Oh, whoops, I forgot to do the octet for the carbon. Okay, now I can count. I have 3 lines for a total of 6, and I have 8 dots. Altogether, that adds up to 14. That's too many. So now I need to erase. I can't erase from the hydrogen. There's no dots to erase, so I can only erase from the oxygen, and I also need to erase from the central to account for it, and I'm going to change the connection between them to a double bond. Now I have 4 lines for a total of 8 electrons and 4 dots. 8 plus 4 is 12, and we're good. Let's move on to this last one. I have 1 bromine with 7 electrons, 5 fluorines with 7 electrons each. Altogether, that adds up to 42. I'm going to put the least electronegative in the middle, bromine, and I have 5-fluorine that goes around it. And already you're probably going, what? This is weird. If I have 5-fluorine, already bromine is breaking the octet rule. Let's go check our exceptions. I have here listed out some exceptions to the octet rule. The ones in the third period and beyond tend to have more than 8 electrons because they have empty 3d orbitals, which is the expanded octet rule. It doesn't mean they have to have more, but they can have more. One of the atoms that can have more is bromine, which can have 8, the octet rule, or it could have 10 or 12. So it's okay that bromine is going to end up with more than 8 because we see that it's allowed to be an exception. So let's keep going with our process. We're going to go ahead and complete the octets for all of the outer atoms. A little time consuming, but we fill them in. There we go. Now we're going to count what we have. I have 5 lines for a total of 10 valence electrons, and I have 6 dots around each of the 5 fluorines, which comes out to 30 dots. Altogether, I have 40 valence electrons in this structure, and I'm supposed to have 42. In the past situations, I knew what to do when I had too many, but in this case, I don't have enough. But then I go back and I remember, isn't bromine able to have 8, 10, or 12? Well, currently it already has 10, so I can just go ahead and add 2 more on bromine to give it 12, and that's okay. And now when I count everything up, it gives me the 42 that I'm supposed to have. So yes, there are some exceptions to the octet rule, and I would make note of them, especially the ones that are listed here. But for the most part, everything follows that octet rule, and they're pretty easy. I hope that you have better luck with doing Lewis dot structures because it does really help you to understand the behavior of these molecules. Again, I'm going to have a link to this PDF with all the steps and examples in the notes below.